Hello everyone, and thank you all for joining me here today. My name is Dan, I'm very happy to be here, and today I'll talk about Kotlin symbol processing. So in today's talk, I'll try to explain what KSP is, how it works, and when you should consider using it. So I hope you'll enjoy this talk and learn something new. Before we get into the topic, I'd like to start by giving you a bit of background about myself. So I'm doing Android development for 7 years now. And to put that into perspective, when I started doing Android development professionally, Samsung Galaxy S8 and Pixel 2 were flagship phones. Currently, I work for a company called Endava, and previously I was part of a company called Five, which was officially Google Developers Certified Agency in 2018, which was later acquired by Endava. During this time, I've been lucky to work on large projects that have reached millions of users, with over 20 million downloads and more than 5 million users using our apps every day. Outside my day job, I also worked on a couple of book projects and numerous tutorials, and I also given talks at large international conferences such as droidcon. So today, I'll talk about Kotlin symbol processing. So let's get into the topic. What is Kotlin symbol processing, or KSP? KSP is a new way to do metaprogramming in Kotlin. But what is metaprogramming? In simple terms, metaprogramming means doing something else with the code you wrote. So metaprogramming is a technique that allows programs to inspect, modify, and act on their own code. Key features of metaprogramming include inspection, transformation, and code generation, meaning that the code can analyze itself, modify itself, or even produce new code. Metaprogramming adds flexibility to code by allowing it to adapt to changes without manual intervention, and it also adds efficiency to code by reducing repetitive boilerplate code and enabling automation of tasks. Kotlin already supports several forms of metaprogramming. The first one is reflection. So, for example, you can use reflection in Kotlin to inspect class properties during runtime. Second form of metaprogramming is annotation processing. So Kotlin uses annotations to add some metadata to code, and these annotations can later be processed to influence code generation or compiler behavior. And Kotlin also allows you to create your own custom annotations. And the third way of doing metaprogramming are compile plugins. So compile plugins are powerful tools that extend compiler's capabilities and allow for code transformation during the compilation stage. Compile plugins basically enable more advanced code manipulation and code generation techniques. So annotation processing is the most popular form of metaprogramming. Why can't we just use Kotlin's annotation processing tool? Kotlin's annotation processing system is a system that's inherited from Java ecosystem, and this allows developers to easily migrate their tools from Java to Kotlin. However, this integration comes with a cost. Since annotation processing operates on Java language constructs, Kotlin-specific features such as properties or top-level functions are not directly supported. And to work around this, build toolchain performs some tricks to enable this integration. However, this leads to performance issues during build times, and it can also sometimes generate confusing error messages. Another significant limitation of KAPT is that it is closely tied to Java ecosystem. So this means that annotation processors can only be used on the environments where Java is the target runtime. What about compile plugins? So compile plugins are extremely powerful, and compile plugins allow you to make extensive changes to the behavior of the language and to the generated code. However, using compile plugins also comes with some downsides. The APIs provided by Kotlin compiler are not guaranteed to be stable. So this means that these APIs can change with each new version of the compiler. Also, using these APIs requires in-depth understanding of compiler technologies and specific implementation of Kotlin compiler. And lastly, there's very little documentation on compile plugins. So there's no an official guide on how to create a Kotlin compile plugin. You basically have to go to the existing Kotlin code and understand it yourself, which is not that straightforward. And this is where KSP comes into play. So KSP is a new meta-programming tool built by Google that understands Kotlin-specific features. KSP is not tied to the JVM, so this means that it can be adapted to work on other targets such as Kotlin Native or Kotlin JS. KSP is significantly faster than KAPT, so KSP reduces build time overhead that's imposed by KAPT. And lastly, KSP provides powerful yet easy to use API. We're going to see that on an example later on. When you look at the promotional materials from Google, they claim that KSP is up to 2 times faster when compared to KAPT. Specifically, they're claiming that they're seeing performance improvements of processors like Room of up to 2 times when migrated to KSP. I haven't done any benchmarks myself, so I can't verify how accurate this is. Most of the popular libraries on Android already support KSP, and more are under development. So to check out the full list of libraries that support KSP, you can visit the following link, since this list is constantly being updated. Now, what are some use cases for KSP? Code generation is primary use case, where symbol processors are used to generate new source code files, which reduces manual coding effort. So, for example, Room persistence library on Android does exactly this. So it uses code generation to generate an abstraction layer over an SQLite. Second use case is code validation. So processors can enforce some rules and constraints during compile time, such as checking for API misuse or ensuring that the required annotations are present. So this helps prevent runtime errors, and it also helps catching issues early on in the development cycle. And beyond code, KSP can be used to generate other types of resources, such as JSON or XML configuration files. In general, KSP can be used to save time and reduce errors by automating repetitive tasks. Let's now get into the basics of how KSP works. So when you first start working with KSP, first thing you have to do is you have to apply KSP Gradle plugin in your Gradle files. Since KSP Gradle plugin is hosted on Maven Central, you have to tell Gradle to search in Maven Central when applying the plugin. Next, you have to specify KSP version that you're going to use. Important thing to note here is that each KSP version is strictly tied to the exact Kotlin compiler version. And for this reason, KSP version string has a Kotlin version in it. And now you can apply KSP plugin in the module where you're going to use KSP. So you have to apply the plugin, and you have to specify symbol processors that you're going to use in that module. In our case, we are adding 2 symbol processors. The first one is a third-party processor from the Room persistence library, since we are going to use this library, and the second one is our custom symbol processor that's defined in a separate module inside of our project that we are going to implement later on. So when adding symbol processors to your module, you're basically adding that as you would add any other dependency, except that instead of using implementation or API functions, you're using KSP function. Let's now take a look into how KSP models Kotlin code. One of the design goals of KSP was to support Kotlin naturally, and as such, KSP's interfaces are modeled after Kotlin grammar. So this means that if you are familiar with Kotlin language, you should be able to use KSP API with relative ease. And let's now take a look into conceptual example on how KSP models Kotlin class with its functions in a file. So when you have Kotlin class like this, KSP will give you access to symbols representing these elements. So when KSP starts processing this file, it will use my example class as a class declaration. So in KSP, KS class declaration interface models class declarations. So this includes classes, interfaces, and objects. And for each class declaration, you can query for further details, such as member declarations, for example. KS function declaration interface models function declarations. So in our case, we have two KS function declaration nodes representing myFunction1 and myFunction2 functions. Again, for each function declaration, you can query for further details, such as visibility modifiers, for example. We can also note here that KSP models Kotlin code by building a tree of nodes from our source code. And each of these nodes represents a structural element according to the Kotlin language grammar. So the example we looked at was a simplified example on how KSP models Kotlin class with its functions. The full class diagram that KSP works with is more complex. So KSP's class diagram doesn't only include class and function declarations, but also properties, annotations, type parameters, and more. So in the screenshot and the link provided, you can check out the full extent of the class diagram that KSP operates with. In KSP, references to types are designed to be resolved explicitly by processors, because type resolution is one of the most expensive operations in Kotlin compiler. So whenever you reference a type in KSP, it's always going to be of KS type reference. And much of the information is actually available without resolution. So for example, type arguments can be obtained from KS reference element. If the original declaration referenced by KS type reference is needed, it can be obtained by resolving to KS type and accessed through KS type.declaration. However, processors should only resolve to a type when a specific information from KS type or KS declaration is needed. Now, KSP also comes with some limitations. So for simplicity and efficiency, no modifications to the existing code are allowed. So processors are only supposed to generate new source code files, which are then compiled together with the original source code. Also, no expression level information is available to processors. So KSP can get you further than a declaration. All that KSP can see or examine are structures of classes and signatures of functions. So let's now get into the practical part of this talk. So what are we going to build today? For the purposes of this talk, I built a very simple application that demonstrates the capabilities of KSP. So in this slide, you can see the QR code and the link that will take you straight to the repository of this project. So all of the code samples and code snippets that I'm going to show in this presentation are simplified code snippets taken directly from this repository. So I encourage you to dive deeper into this repository later on to see how a bit more advanced use cases and some extra edge cases are handled. So the application I built is called People Hub, and it's a very simple application with a single feature. So all that this app does is that it stores a list of people into a local database on a device. So it has a screen that shows a list of people from a database. It has a screen that allows you to add a new person into a database, and it has a screen that shows some additional info about a specific person. What we are more interested about here is the architecture of this application. In many common architectural approaches, such as clean architecture, for example, we create software models of entities from our business or problem domain. And depending on the size of our project, we often define multiple layers inside of our project, where each layer works with its own data models. So a common variation that you can find in projects are API models, database models, domain models, and so on. And each of these models can describe the same initial entity. In our case, since our application stores data into a local database, we are going to work with database models, which represent database entities, and we're going to have domain models that the rest of the app works with. So for simplicity, we are only going to work with two types of models. And this is how these models look like in code. So first we have a person data class, which is a domain representation of our person. And then we have a person entity data class, which is a database representation of a person. In general, when you have multiple representations of the same entity, these representations only differ in a couple of properties, if they differ at all. In our case, for simplicity, these two representations are exactly the same. Since we have two types of models, we also need a way to map between them. And for that, we need these two mapper functions. So the first function maps from the database model to the domain model, and the second one maps from the domain model to the database model. Now, we don't want to have these mapper functions as a top-level functions, but instead we want to hide the mapping logic behind an interface. So for that, we need some kind of mapper interface component and mapper implementation class, which implements mapper interface. So mapper interface defines mapping methods, and mapper implementation class implements these methods, and it contains the actual mapping logic. So in order to map between our database models, we need this mapper component. And we could write this component manually by ourselves, since it's pretty straightforward to do, and it doesn't take a lot of time. However, it would be nice if we could somehow, so if we decide to change our models, for example, we decide to add new properties to it, we would also have to update our mappers as well. So it would be nice if we could somehow automatically generate these mappers. And that's exactly what we are going to do today. So we are going to use KSP to automatically generate this exact mapper component based on annotation in our code. So let's get into it. First, we have to set up KSP within our project. Our project consists of three main modules: app module, annotation module, and processor module. App module is the main module of our application that contains business logic and UI. So it's the core module that the end user interacts with. Annotation module is a module where our custom annotations are going to be defined. So these annotations will be used by the app module to indicate that some component needs some kind of code generation or code processing. And processor module will contain KSP code. So processor module will contain logic that will act upon our custom annotations. And yeah, so processor module depends on the annotation module because it will use the annotations defined in the annotation module, and app module depends on both annotation and processor modules because it will use the annotations defined in the annotation module, and it will use processors defined in the processor module. So first, we are going to define a custom annotation that we called generate mapper. So we are going to use this annotation to annotate data classes that need their mappers automatically created. This annotation takes in one parameter named name. So the value of this name parameter is going to be used as the name for our mapper interface component. We're also using two meta annotations here: retention, and we are specifying source as the annotation retention. So this indicates that this annotation is only needed at the source level and not in the runtime or in the binary outputs. We're also using target meta annotation here and specifying class as the annotation target. So this indicates that this annotation can only be applied to class declarations. Next component that we need is a symbol processor provider. Symbol processor provider is a component that allows us to create an instance of our custom symbol processor. So to define a symbol processor provider, we have to create a new class which implements symbol processor provider interface, which is part of KSP API. When implementing this interface, we have to override the create function. Create function will be called by Kotlin symbol processing to create an instance of your custom symbol processor. So in our case, we are creating an instance of mapper generator processor, which is our custom symbol processor that we are going to implement in the upcoming slides. When it comes to the symbol processor provider, there are a couple of rules that you need to follow. So each symbol processor provider needs to be specified in a special file named com Google DevTools KSP processing symbol processor provider under the source main resources meta-inf services path. And the content of this file needs to be fully qualified name of your symbol processor provider. So all of these three rules need to be met in order for symbol processor provider to work as expected. And now we can define a symbol processor. So symbol processor is the main component that will contain the logic for code processing or code generation during compilation. To define a symbol processor, we again have to create a new class which implements symbol processor interface, which is again part of KSP API. In our case, our mapper generator processor takes in two parameters, code generator and logger, which are used for creating new files and logging respectively. When implementing symbol processor interface, we have to override the process function. So the process function is where the main logic for code processing or code generation will live. Process function takes in one resolver parameter that gives us access to the program structures, such as symbols representing classes. And inside of our process function, all we do currently is we log a simple informational statement so that we can later verify if everything is set up correctly. In our case, process function returns an empty list. So this list represents a list of symbols that couldn't be processed in this round and should be deferred to a later round of processing. So KSP supports multiple round processing, but that's a bit advanced topic and it's out of the scope of this talk. And that's it. Now we can verify if everything is set up correctly. So to do that, we can run this Gradle command. This command will clean build directory of our project, and it will assemble the debug variant of our application. We also have to specify this info flag here to make sure that the logs that we print from our symbol processor are being visible in the console output. And if we run this command, and if we check for KSP logs, we are going to see that the logs that we print from our symbol processor are being visible in the console output. So this indicates that our symbol processor is being invoked during compilation and that everything is set up correctly. We can also look for the generated files under the build generated KSP directory, since this is the directory that will contain generated files. For now, we are still not generating anything, so this directory is going to be empty. So when it comes to this symbol processor, resolver is the main component. Resolver retrieves code symbols and their associated information. So for example, we can use get symbols with annotation on the resolver instance to get all of the symbols that are annotated with specific annotation. So usually the first line of most processors is likely going to be a call to some method on the resolver instance. And there are also other useful components of KSP that are commonly being used. So code generator, which is responsible for generating files, logger, which we already used, which provides logging capabilities, and you can also pass in some extra processor options to allow for customization of the processor's behavior. So we are going to use our custom generate mapper annotation to annotate all of the data classes that need their mappers automatically created. So first, we have to get access to all of the classes that are annotated with our annotation. The logic for that will live inside the process method of our symbol processor. And first thing we have to do is we have to get the fully qualified name of the annotation that we are interested in, which in our case is generate mapper annotation. Then we can call get symbols with annotation on the resolver instance, pass in the annotation name, and convert the result into a list. So this will give us a list of symbols that are annotated with generate mapper annotation. Since we are only interested in class declarations, we can further filter result symbols to only include instances of KS class declaration. So this will give us a list of all of the class declarations that are annotated with generate mapper annotation. And to verify if this works as expected, we are simply going to print all the items of the class declarations list to the console output. And if we build our code now, and if we check for the console output, we're going to see that there's only a single class that's annotated with generate mapper annotation, and that's our person entity data class. So this is what we are expecting to see. And now that we have access to all of the classes that need their mappers automatically created, we can start generating these mappers. To do that, we are going to use KSP API and Kotlin Poet library. Kotlin Poet is a library developed by Square that simplifies generating Kotlin code and makes the whole process more efficient. So Kotlin Poet provides abstractions for Kotlin syntax, and it allows us to create constructs such as classes, functions, or basically any other Kotlin language construct, which makes the whole process of generating Kotlin code more simple and more intuitive. Let's take a look into an example on how we will generate a simple data class with and without Kotlin Poet. So to generate this person data class without Kotlin Poet, we have to use string manipulation and string concatenation operations, and we have to handle things such as importing, escaping, and formatting manually. So we can see that this code is not very readable, scalable, or maintainable, and if we wanted to add more features here, we would end up with even more complex and error-prone code. Kotlin Poet provides us a way to allow us to use builders to generate Kotlin code, and it handles things such as importing, escaping, and formatting automatically. So this code block will produce exactly the same output as the above code block, but with a much more simpler and cleaner syntax. Okay, so next thing we have to do is we have to extract the value of the name argument from our annotation, because the value of the name argument is going to be used as the name for our interface component. And this is how we can do that. So let's go through this code block. So first line gives us access to all of the annotations that are applied to a specific class declaration. Then we are going through these annotations, and we are trying to find an annotation whose fully qualified name equals to the generate mapper annotation, because this is the annotation that we are interested in. If such annotation is found, we are going through arguments of this annotation, and we are trying to find argument named name. And if such argument is found, we get the value of this argument, and we convert the result into a string. So this will extract the value of the name argument from our generate mapper annotation. So for example, if we have this person entity data class that's annotated with generate mapper annotation, and we used dbMapper as the value of the name argument, if we built the previous code block and check for the console output, we are going to see that dbMapper name is being extracted correctly. And now that we extracted the name for our mapper interface, we can start generating the actual interface and implementation class components. So to create an interface in Kotlin Poet, we can use typespec.interfaceBuilder and pass in the name of the interface. And to generate a class, we can use typespec.classBuilder and pass in the name of the class. So the name of the class is the same as the name of the interface, except that it contains this impl suffix. We're also adding some extra properties to our class. So we have to specify that our class implements the interface, and we are doing that using add superinterface method. And we are also adding internal modifier to our class using add modifiers method on the class builder. So this gives us access to the interface and implementation class builder components. When we have these builders, we can write them into a file. In Kotlin Poet, file spec represents a file. So we have to create a file spec instance, and we can do that using filespec.builder and pass in the name of the file. After that, we can use addType method to specify the type that we want to write into this file. So the type that we're writing into a file are the builders that we created on the previous slide. And finally, we are calling a build method on the file spec builder to get the file spec instance. And when we have a file spec instance, we can write it into a file using a write_to method on that instance. Write_to method takes in two parameters, code generator and a Boolean flag. Code generator represents a path to which this file is going to be written, and Boolean flag represents that we want to overwrite any existing file with the same name if it already exists. And if we build our code now, we are going to see that two files are being generated, dbmapper interface and dbmapper implementation class, which implements dbmapper interface. So for now, these two components are empty. They don't contain any functions. So let's add some functions to it. So we'll start with the interface function. To create a function in Kotlin Poet, we have to create an instance of funspec. To do that, we can use funspec.builder and pass in the name of the function. Since this is an interface function, we have to add an abstract modifier to this function. Abstract modifier indicates that this function has no implementation, so it has no body. We also have to add a parameter to this function. Parameter consists of parameter name and parameter type. The type of the parameter is a type of the class from which we are mapping. We also have to specify a return type, and return type is a type of the class to which we are mapping. And finally, we are calling a build function on the funspec builder to get the actual funspec instance. When we have a funspec instance, we can add it to the interface by using addFunction method on the interface builder. And if we build our code now and check for the generated dbmapper interface, we are going to see that it has one map_to_person function. So we also have to add the same function to the implementation class as well. The code for that will be very similar with two differences. The first one is that instead of using abstract modifier, we have to use the override modifier because the class function implements the function from the interface. And of course, the class function contains the actual mapping code. So we have to add a code to this function, and we can do that by using addCode method on the funspec builder. addCode method takes in a call block instance. A code block represents a block or a segment of code in Kotlin Poet. And to create a call block instance, we can use callblock.builder. And then we can use add method to add the actual code to this call block. And finally, we are calling a build function on the call block builder to get the actual call block instance. To keep the slides short, I'm not showing the actual code that we are adding to this call block since there's nothing KSP specific in it. And if we build our code now, we're going to see that the generated dbmapper implementation class contains map_to_person function which overrides from interface, and it contains the actual mapping logic. And this is how we can automatically generate mappers based on annotations in our code in the native Android project. But what about multi-platform? So can we use KSP in multi-platform projects? Yes, we can, but a build configuration is a bit different in this case. So instead of having a dependencies block for each compilation target, we have to define a special top-level dependencies block, and there we have to specify which compilation targets need symbol processing. So for example, to specify that common and JVM targets need symbol processing, we can use the following dependencies block. And that's it. So to wrap things up, we are briefly going to look into what are the future plans of KSP, and we're going to go through key takeaways of this talk. So future plans of KSP focus on three main areas. First one is to support new Kotlin compiler. If you're working with Kotlin, you know that with Kotlin 2.0, we also got the new K2 compiler. So KSP also needs to be adapted to work with the K2 compiler. Good news is that KSP2, that supports K2 compiler, is already in beta, but there's still more work to be done before a stable release. Other plans focus on expanding multi-platform support and improving performance. So I already mentioned that KSP is significantly faster than KPT. However, there are still a bunch of optimizations that can be done. And to recap, stop using KPT and prefer KSP where possible for performance reasons. In this talk, we only covered the basics of KSP. So we only showed how to generate some mapper interface and mapper implementation class based on annotation in our code. However, KSP is much more powerful than this, and it contains much more advanced features. So I encourage you to dive deeper into KSP and explore how it can benefit your work and help you save time and reduce errors by automating repetitive tasks. And that's all. Thank you all for your attention, and if you have any questions, you can find me after the talk.